All right. So just indulge me here for a minute. Let's go back to where we were kind of at the end of yesterday. We kind of stopped in the middle of something that I didn't want to carry us too far deep into it. We started to talk about the idea of rate laws. And in rate laws, again, what we're trying to do with rate laws, we're trying to set up a quantitative relationship between concentration of reactants and the speed of the reaction itself. And we talked about the idea of orders, reaction orders being what is that mathematical relationship? Is it a relationship of zero impact? Well, then it's zero order. Is it a relationship of linear impact? Well, in that case, it would be first order. Or is it a relationship where it seems to be almost exponential? Then that would be second order. Um, but one thing that we want to be really careful about with regard to rate laws is that rate laws themselves are not related specifically to the stoichiometry. So case in point here, we have this reaction where dinitrogen trioxide is decomposing. We can see that even though the stoichiometric coefficient is 2, the rate law is not second order for the dinitrogen trioxide. It's in fact first order. And here we have a reaction between trichloromethane and chlorine. And we see that it's first order in the trichloromethane and 1/2 order in chlorine. Now, just a word about that. We're not going to get into half and fractional orders in this class. That's a higher level. I actually don't remember seeing fractional orders for very long or very much until I got into graduate school kinetics. So don't worry about seeing that kind of stuff here. That's something that you would only worry about if you took chemistry all the way to graduate school, which most of you probably will not. But we can see here in the last reaction, hydrogen and iodine making hydrogen iodide. It is first order in each of those. When that kind of thing happens, it is more of a coincidence than it is an actual expression of normal reality. When we talk about mechanisms on Monday, we'll discuss this kind of situation. What we'll find out is that most reactions take place in multiple stages, where one reaction happens and then another reaction happens and then another reaction happens. And as we go from step to step to step, we eventually get to the products, but it's not always in the most direct way. Reactions like this, where the rate law matches the stoichiometry, are examples of the somewhat rare circumstance where a reaction is single step, where there is not a multiple step mechanism, but rather a one-step mechanism. This molecule and this molecule collide, and when they collide with the proper force and orientation, we get the exact products that we were looking for. And we don't need to do anything else. So let's take a look at this relationship. And let's do a little bit of calculating here to try to understand the relationship more fully. So we've got a reaction between A and B to make C. The stoichiometry is that 2B react with A to make C. But the rate law is second order in A and first order in B. And so what we want to do is we want to explore what happens to the reaction rate when I start changing the concentrations of these things. So for example, if I hold A constant, but double the B, what is the expectation for what happens to the rate? Well, I need to look at the rate law. The rate law says that B is first order. So since B is first order, we know that the relationship is linear. If A is being held constant, so it's not going to impact the change in rate, B doubling is going to also double the rate. It's a linear relationship. The change that took place in the reactant is going to be reflected in the change of rate for the reaction. In this second example, here I have A that is doubling while B is held constant. And now I look at it and go, okay, well, A is second order. So if I am doubling my concentration, the impact is going to be 2 squared. Two squared is 4. So the rate is going to increase by a factor of 4 because it is second order. And the same logic applies here as well. If A is halved when B is held constant, well, now we're doing 1/2 x. 1/2 squared is 1/4. That reaction is now going to go at quarter speed. So it would decrease by a factor of 4x. Now, what if we were manipulating both at the same time? Let's add an extra one here. So if the concentration of A is doubled and the concentration of B is tripled, what's going to happen? Well, basically, we're just going to do the 2 different manipulations, but then we're going to multiply them together because the rate law multiplies together those concentrations. So doubling A would get an increase by a factor of 4. And then for B, because B is first order, the A concentration would quadruple the rate. The B concentration would triple the rate. The 2 in combination with each other would increase it by a factor of 12. And so when we start looking at the kind of concept of, well, how do we handle these kinds of problems? What is the impact of this going to be versus that? The rate law is going to tell us a lot of that information. All right, any questions so far? All right, so let's move it over to Top Hat then. All right, the question is, we have a reaction that is first order for A and second order for B. What happens to the rate if the concentration of B is cut in half? And so this is a multiple choice question here. And yeah, so we're on the right track here. If we're looking solely at B, B's concentration was 1/2 of the original. We would be squaring that because it's second order, so that would be 1/4. So decreases by a factor of 4, or by 1/4. Either way makes sense. All right, let's look at the next one. Now we have a reaction that is first order to A and second order to B, so just like the last one. What if B is cut in half and the concentration of A is double? So just like the example that we wrote into that previous slide, we're going to need to take both in turn and figure out how they come together. So one way that we can do this is we can kind of create a hypothetical. So let's just say for the sake of argument that the concentration of A and B are both 1 for this first example. And if that is the case, then we would have the rate is equal to the rate constant times 1 to the first and 1 to the second. So that would just be K. Now in our second scenario, where we are applying this change, let's call that condition R star. We have K times, we doubled A, so now this is 2 to the first, and we cut B in half, so this is now 1/2 to the second. Well, that would be equal to K times 2 times 1/4. 2 times 1/4 is 1/2. So if I'm comparing my second rate, the one that has the conditions specified in the problem, has half of the rate of the first one. And so that should have given us letter D here, and good, we're all there. Okay, so the rest of today is going to be spent discussing really 2 different ways that we can express the rate law and find the rate law using experimental data. And next week in lab, our Monday labs are going to kind of explore both ends of this, where we start to look at, we'll do a lab where we use the method of initial rates, and we'll do a second lab where we use the integrated rate law. And so for the rest of this first hour, we're going to focus on the method of initial rates. And I'm going to show you a couple of different ways to do the work. And then we'll do a bunch of example problems to kind of close it out, which will help you with your homework. So in the initial rates method, what we're doing is basically kind of what we described in these early practice problems. We're going to run the reaction several different times. And each time we run the reaction, we're going to change something a little bit different about the experiment itself. So if you look at these 3 experimental runs, you can see that we've kind of done run number 1 and established a baseline. We've done run number 2 where we changed the concentration of one of the reactants. And then in run number 3, we changed the concentration of a different reactant. And so what we're trying to find here is our generic rate law looks like this. The rate of reaction is equal to K, the rate constant, multiplied by the concentration of A to its order, whatever it is, multiplied by the concentration of B to whatever order it is. And so we need to use the experimental data to try to figure out what the values of X and Y are to figure out the orders of reaction. Now, there are 2 different methods for going about this. And you can use, let me tell you this. The second method that I'm going to show you is more complicated. It's more calculation oriented. It also works every time. The first method I'm going to show you is called the inspection method. And the inspection method works great for problems like this, where it's very easy to see how we manipulated the variables, and it's also very easy to see the impact of that manipulation on the reaction rates. The numbers are very easily multiplied and divided. You don't need to do a whole lot of brain work to figure out what's going on in the problem itself. And so we'll start with that method, and then I'll show you what the calculation method looks like so that when you come up across those problems that are a little bit more complex, a little bit more difficult to do, you've got that backup plan where you know what to do when things get tough. But we'll start with inspection. The inspection method kind of just asks us to look at, okay, what did we change and how did that impact the reaction rate? So I'm going to compare experiments 1 versus 2 here. And what I can see is that in experiment 1 versus 2, I can see that we doubled the amount of A without changing B. So this becomes exactly the kind of problem that we just did. What is the impact on the rate if such and such happens? The only thing is that we don't know what the order is yet. We know what the change in rate is instead. So we're kind of working in the opposite direction. But we can see that the initial rate did not change, even though we changed the concentration here. So what does that tell us about the order of A, since its concentration did not have an impact on rate? Yeah, it's 0 order. And so in the A column here, I'm going to write 0. And so since A is 0, again, if I'm drawing this out, that was my generic rate law that we started with. I've now determined that A is 0 order. I haven't figured out what B is yet. But because A is 0 order, do we need to include it in the rate law? What is anything to the 0th power? 1. And since anything to the 0th power is 1, it doesn't matter what number I put in there. It's always going to calculate out as 1. So I'm going to remove A from the rate law now. Because since we've determined it's 0 order, we know it has no impact on the rate at all. So why include it? This is where we have to kind of keep reminding ourselves. Rate laws are not chemical equations. Rate laws are not tied to stoichiometry. Just because something is a reactant doesn't mean it has to be in the rate law. The rate law is only giving us the relationship between things where we see concentration changing and how they change the rate of the reaction. Now, since A is 0 order, I actually can ignore it from now on if I wanted to. But let's just pretend for the sake of argument that we couldn't. Let's pretend that we had a first order kind of determination there. What would we do? Well, we would do something like this. My next thing would be to compare runs 2 and 3. because in runs 2 and 3, I can see that A is not changing and B has increased by 2x, and that's not showing up on the screen very well. Let me fix that. Right, better. And we can see that the reaction rate here has also doubled. So if A were not zero order, if it were second or first order, we would want to find another isolated case where A was being held constant. In this particular instance, it really doesn't matter because since it's zero order, you can have any concentration at once, it's not going to matter. But that impact does. I've doubled the concentration and I've seen a doubling in the rate. The two are changing by the same factor. And that should tell you what about the order for B? It's first order. So, the words that you need to continue to tell yourselves over and over again: zero, linear, exponential. Those are the three orders. No impact, linear impact, exponential impact. If they change by the same factor, it's first order. So now that we know what the order is, our rate law is now completed, where we know that it is first order in B, and that's all that's there. The rate law is equal to K times concentration of B to the first power. So that's the inspection method. And like I said, the inspection method works great when I have very concrete numbers that are easy to see how they have been manipulated. It's easy to see off of this. I didn't need to break out my calculator at all to know that the concentration doubled and the rate doubled. Now, what do you do if it's not this easy? What if you have numbers that are a little bit more complex and a little bit more difficult to work with, where I can't really tell just by looking at it if it's doubled or tripled or quadrupled or anything like that? This is called the calculation method. It has its roots in the same kind of way. You're going to start by picking two reaction runs that have similar kinds of characteristics, meaning where something's being held constant. But what you're going to do instead is you're going to take those two reaction runs and you are going to divide them by each other. So we take the information from experiment 1, we write out its rate, and we fill in all the blanks. So instead of A and B, we would put in the actual concentrations from the table. And then we take our second reaction and we do the exact same thing. So if we follow this all the way through, so The first comparison that we did was reaction 1 versus reaction 2. And so I can see R1 on top, R2 on the bottom. Since we've picked reaction runs where things are being held constant, this 0.1 to the y term is in the numerator and the denominator, so it cancels. K, if we're not changing temperature, K is going to be the same as well. So they cancel. All that we have left is the ratio of rates, which, again, my units now cancel. So all I've got left is just 0.002 divided by 0.002. That's how we get 1. And we skipped a step here. You may remember from algebra that if I have a fraction with an exponential term in the numerator and the denominator, I can bring them all in under one house. Raised to that exponent. So if you're wondering how we got to 0.5 to the x off of that fraction, because it looked like the fraction wasn't going to cancel out, that's the step that was missing. Now we've got to apply a algebra 2 concept. How do you get rid of an exponent? Well, you've got to take the logarithm. Take the logarithm of both sides. And so log of 1 is 0. Taking the logarithm of this side, it becomes x times the log of 0.5. Well, in this case, it really doesn't matter. The only way that you get 0 out of that is if x is equal to 0. And so we calculate that x is equal to 0. We would then say that a is 0 or for b, we would effectively do the same thing. Now, like I said on the previous slide, since we've determined that A is 0 order, technically we do not need to include A terms once we've made that determination. But if we, again, isolated variables here, so we've got run 2 versus run 3. Again, k's will cancel out. 0.2 to the x's will cancel out. Point 0.002 divided by 0.004 is a half. Okay. That didn't come out correctly. This is supposed to be 1 to the x times 0.5 to the y. But we're basically in the same position again. We know that this has canceled out, so we can get rid of it. 0.5 to the y, we take the logarithm of both sides. We end up getting y is equal to the log of 0.50 divided by the log of 0.50, which we would recognize that as 1. And so we would conclude that B is first order as a result. So like I said, this is the way to do it mathematically. And you can see when the numbers are simple, it makes no sense to go through and do all this logarithm nonsense because you can see where it's going before you even get to the log stage. But when the numbers are more complicated, when the numbers are not as cut and dry, or when you're using your own data as opposed to one of these carefully constructed book examples, it doesn't often come out exactly this clean. And so the calculation method is a good backup method to fall upon when it's not blatantly obvious what the factors are when you're trying to do it by inspection. Now, the other thing that we can do out of this is once we know what the rate law is, we can now use the information from that data table to figure out what the value of the rate constant is. What is K? And to do that, we just take what we're given. So we know that rate is equal to K times B to the first. And so we just plug in the values from the data table. So I go back to the data table. The data table says that the rate was 0.002 and B was 0.01. So 0.002 molar per second is equal to K times 0.01 molar. I do the division, 0.002 molar per second over 0.01 molar. I see that the molar concentrations cancel. So my unit here is going to be in reciprocal seconds. So if I put it all together now that I have this value of K, then we get R is equal to 0.2 reciprocal seconds times the concentration of B. Now, one thing that you will notice out of this You can always tell the overall order of reaction based upon the units of the rate constant. Because since the rate is always going to be given to us in molar concentration per second, the unit for the rate constant is always going to be such that it matches whatever number of molar concentrations it has to be multiplied by. So if it's first order, it's going to be just reciprocal seconds, because molarity times reciprocal seconds gives us molar per second. If it's zero order, it's going to be molar per second, because there are no concentrations that it's getting multiplied by. If it's second order, then we're going to see per molar per second, where I've got molarity in the denominator. And so since I'm multiplying by two molarities, the first one cancels out the one in the denominator, and the second one becomes the molar per second, and so on and so on and so on. So you can always know the overall order of a reaction by looking at the rate constant. Now, that doesn't necessarily give you the rate law, but it does tell you how many concentration units are going to be in it. It's going to tell you what the order is. All right, let's take a look at some other examples here. And so with this one, we are trying to determine the rate law for this reaction. And we can see that the numbers here are relatively straightforward. So let's try to do this by inspection. So I can see in experiments 1 and 2, BF3 is being held constant. Ammonia has been cut in half. What happened to the rate? It's been cut in half as well. Now, if you can't do the number math in your head that quickly, it's perfectly okay to just break out your calculator and say, okay, 0.1065 divided by 0.213, yeah, that's a half. So what's the order for ammonia then? We cut its concentration in half, the rate decreased by half. First order. The impact is identical. What I did to the concentration happened to the rate. That's the definition of first order. So we know that ammonia is first order. Okay, now we need to find a scenario where ammonia is being held constant so that we can look at the impact of the boron trifluoride. Now we've got lots of options here to choose from, but let's do the same thing. Let's find a place where ammonia is held constant, and then let's be choosy, because there are 3 places where it's held constant. Where is the number the easiest to work with? I'd say it's between 4 and 5. So I can see that the ammonia is being held constant. The boron trifluoride has been cut in half. And I think that's a half. Let me double check. 0.0596 divided by 0.1193, 0.4995, close enough. So what is the order of the boron trifluoride? It's also first order. I changed its concentration. The rate changed by a similar factor. That's the definition of first order. So we have determined that each of our reactants is first order. So the rate law is going to be K, the rate constant, times boron trifluoride to the first power, times ammonia to the first power also. That is our rate law. Now, can we take this one step further? Yes, we can find the value of the rate constant as well. The value of the rate constant, doing a little bit of quick algebra, would be equal to the rate over the concentration of BF3 to the first and ammonia to the first. I can choose any reaction run to do that calculation for me. Easiest, most convenient is usually just to stick with the first one. So 0.2130 molar per second divided by 0.250 molar and 0.250 molar. So we can see that the molarity in the rate has canceled one of those molarities, but not the other one. Which means that for this second order reaction, the rate constant is going to have a unit of per molar per second, which we can also write as, if you prefer to keep it in fractions instead of exponents. What's the numerical value? 0.2130 divided by 0.25 divided by 0.25 to three significant figures, 3.41. And so if we wanted to further specify this rate law, we could put that in 3.41 per molar per second times the concentration of boron trifluoride to the first times the concentration of ammonia to the first. Questions here? All right, let's do another one. And this time, I'm going to let you kind of drive the bus on this. So go ahead and try to work this one out on your own. Feel free to use the inspection method if you feel that it is possible or warranted to do so. If not, you've got the calculation method to fall back on. And understand, you can mix the methods too. So if one of them is easily solvable with mix or with inspection, do it by inspection. It's way easier. All right, so most of you kind of skipped to the nitrogen, which was the smart thing to do. And you recognized, okay, well, this oxygen's being held constant. The nitrogen decreased by a quarter. And if you do the math, 496 divided by, or 124 divided by 496 is also a quarter. You recognize pretty quickly, okay, this is first order. Walking around, pretty much saw first order nitrogen written on everybody's page. Great, fantastic. Okay, now if we take it to the next step then and we look at the oxygen, between reaction 1 and reaction 2, nitrogen is held constant. And we see that oxygen is cut by a factor of 1/2. But 496 divided by 701, that's not a half. That's 0.708. So the question is, well, what do we do with this information? And this is where we fall back on the calculation method. Now, since we've already done the numerical aspect of it, we don't need to set up all the fractions and whatnot. We can kind of skip to the ending. The ending is this: 0.708 is equal to 0.5 to the x. Because that's basically what it is, right? We've got the ratio of rates, 0.708, and we've got the impact of the concentration, 1/2, raised to whatever its order is. If we take the logarithm of everything, it's going to give us the log of 0.708 is equal to x times the log of 0.5. Now we just need to figure out what that value is. Log of 0.708 divided by log of 0.5. And what we get here is the numbers 0.498, which we're going to round to the nearest fraction. So we come up with oxygen being half order. So our rate is equal to the rate constant K times nitrogen to the first power and oxygen to the half power. Now we're being asked to define the value of the rate constant K. So we're going to have to do a little bit of additional calculation here. Remember, K is equal to rate over concentration of nitrogen to the first, concentration of oxygen to the 1/2 power. Does anybody remember or know another phrasing for half power? Exponent to the half. Square root. So you can certainly plug it in, caret 0.5, but you can also take the square root that the two are equivalent. So just taking values from run 1 here, 701 molar per second, 0.04 molar to the first, 0.02 molar to the half. This does get messy. The molar cancels. The molar to the half does not. 701 divided by 0.04 divided by 0.2 to the half power to two significant figures gives us a ridiculously high number, 120,000. And the unit on it would be molar to the negative half, seconds to the negative first. So expanding this, 120,000 So, I'll be perfectly frank with you here. This is about as complicated as it can get in terms of using that calculation method. Like I said, if you kind of understand the fundamentals behind it, you can still even cheat your way through doing inspection for most of these. And if you can't because you don't understand the numbers, you can still use inspection to figure out what the numbers are that you need to take the logarithms of to figure out the order that way. Any questions for the here and now? Okay, so that is the last that we're going to say about the method of initial rates. Let's go ahead and take a 10-minute break, come back at 9:15, and we'll talk about the other technique for calculating, which is the method of integrated rates.